Hey guys, I'm back again with another video on nuclear energy. This is actually a sequel to a previous video I made on the Hillier-Davidson Environmental Awareness Club channel, where I talked about how nuclear energy compared to renewable energy in terms of their environmental impacts. However, in this video I'm going to be focusing a little bit more on the science behind nuclear energy, some of the different types of nuclear reactors. There's a bunch of different stuff very specific to nuclear energy, and that's why it's on my personal channel, is because it's not really relating to the environment in any clear way. So without further ado, I'm going to jump into the video and teach you a little bit about nuclear science and how nuclear power works. First, I'm going to discuss the science behind nuclear reactions, which I think will be simplest to understand if I compare it to the more common and familiar chemical reactions. If you didn't already know, chemical reactions work via the electromagnetic force, which is an attractive force between oppositely charged particles like a proton and an electron pictured, or it can also be a repulsive force between two similarly charged particles, such as two protons or two electrons. Just as chemical reactions rely on the electromagnetic force, nuclear reactions use the strong nuclear force, which is an attractive force between protons and neutrons, as well as quarks inside of those protons and neutrons, but that's a little bit outside the scope of this video. A key difference between the electromagnetic force and the strong nuclear force are the distances on which they operate. For instance, while the force of attraction or repulsion between two charged particles does decrease as the distance between them increases, if you have enough charged particles, you can effectively make the range of the electromagnetic force infinite. This is why at a macroscopic level, you can use a magnet to attract metals to you, and it is also why the Earth is able to have a huge magnetic field around it. On the other hand, the strong nuclear force works only over extremely small distances, though on those small distances is very powerful. For instance, after about the width of 4 nucleons, protons or neutrons, the force of attraction between two particles significantly drops off via the strong nuclear force. This is why two protons that are only separated by two neutrons could be extremely attracted to each other within a nucleus, though if you insert even one more neutron between those two protons, all of a sudden they repel each other very strongly because they have the same charge via the electromagnetic force. This unique characteristic of the strong nuclear force is why the iron 56 nucleus is the most stable one on the periodic table. The iron 56 nucleus has a special property of at no point having a diameter more than 4 nucleons in width. So every single proton will attract each other more strongly via the strong nuclear force than they are repelling each other via the electromagnetic force. Just as in how chemical reactions propel a molecule or atom towards being more stable, nuclear reactions propel a nucleus towards being more stable. This is why every exothermic nuclear reaction works towards making the nucleus more similar to the iron 56 nucleus. And this can either be done via nuclear fusion or nuclear fission, depending on if the nuclei you're working with have more nucleons or less nucleons than the iron 56 nucleus. A cool thing about nuclear reactions that release energy is that the products actually end up having less mass than the reactants. This is also true of chemical reactions that release energy, though it occurs on a much smaller scale because nuclear reactions release far more energy per reaction than chemical reactions do. This is actually due to Einstein's equation of E equals mc squared that helps us understand that energy and mass are two sides of the same coin. So when energy is produced from a reaction, it's because mass is being turned into energy. From my understanding, this is also how potential energy works. It is the extra mass that a substance has that has the potential of being turned into energy of a different kind. Now that I've given you a brief overview of nuclear science, I'm going to transition into talking about how humans have harnessed the power of nuclear energy, particularly in the form of nuclear fission. To start off, I'm going to be discussing the basic components that practically all nuclear fission reactors have. Fission reactors work by having a controlled nuclear reactor within the reactor core that releases energy. That energy is then used to heat up water, converting it into steam. That steam then drives a turbine that generates electricity. This process of using steam to drive a turbine is actually pretty common in power plants, and even power plants like coal plants use this method as well. The first basic component that all fission reactors must have is a fuel source. This is typically in the form of some kind of uranium, but it can also be from other sources like thorium or plutonium as well. For instance, some reactors use uranium oxide pellets that are positioned within fuel rods made of zirconium alloy. These fuel rods are then placed into fuel assemblies, and those fuel assemblies are placed within the reactor core with a lot of them together. The concept of a fuel rod assembly is actually pretty common in nuclear reactors today, though there are other forms that fuel can take. One example of this is liquid salt fuel, which actually incorporates both the fuel for a reactor and the coolant into one liquid. This can be used in things like liquid thorium fluoride reactors and fast neutron reactors. The second basic component of fission reactors are the moderators, which are basically any materials within a reactor that slow down neutrons without absorbing them. This slowing down the neutrons turns them from fast neutrons into thermal neutrons, a concept I'll touch up on a little bit later. But basically, turning these from fast neutrons into thermal neutrons slows them down and makes them more easily absorbed into the nuclei of fissile materials, making nuclear reactions more likely to happen. Like I said earlier, moderators need to slow down neutrons without absorbing them, because the nuclei of fissile atoms like uranium have to absorb those neutrons if nuclear reactions are going to happen. As a result, something like water is actually a fairly good moderator, because the hydrogen atoms in the water molecule are very similar in mass to the neutrons that need to be slowed down, so they're able to slow down those neutrons very effectively. The only problem is sometimes those singular protons in a water molecule will fuse with the neutrons to form a deuterium atom, which is basically hydrogen with one proton and one neutron. To solve this, sometimes scientists will use heavy water, which is water that already has both of its hydrogens as deuterium atoms. And that makes it less likely for the neutron to be absorbed by the hydrogen atom because there's already a neutron there making deuterium. Another good moderator is graphite because, again, it slows down neutrons without absorbing them. Another component of fission reactors that you actually might be familiar with are control rods. Control rods, like the name indicates, are used to control the rate of a reaction by absorbing neutrons. Like I said earlier, neutrons are vital to nuclear reactions because the nuclei of fissile atoms like uranium have to absorb neutrons if they are to split and create energy. Typically, control rods are made of materials like hafnium, cadmium, or boron, which are all very good at absorbing neutrons. And they are placed between fuel rods so that they can stop the neutrons that can go from one fuel rod to another, and thus stop nuclear reactions from happening. Control rods can either be inserted or withdrawn from a reactor core to slow down or speed up a reaction respectively. However, they can also be inserted to completely stop a reaction if needed. To review, this is a diagram that outlines some of the different components that we have talked about thus far, such as the control rods in the top left, the moderator in the bottom left, as well as the fuel elements between the two. In the same diagram, you can see some blue liquid flowing throughout the entire reactor, which you can probably guess is water. In this case, water is not only the moderator, but it is also the coolant. The coolant functions by drawing heat away from the reactor core and taking it to something called the steam generator, where that heat can be used to heat up water, convert it into steam, and generate electricity. In this particular example, which shows a pressurized water reactor, there are two loops. The primary coolant loop, in which the same water is recycled time and time again through the reactor, drawing heat from the reactor to the steam generator, and then going back to the reactor once it has cooled. And then you have the secondary coolant loop, which consists of water that's constantly flowing into the steam generator, where it is converted into steam and used to turn a turbine and generate electricity. Another important component of fission reactors is the pressure vessel, or in some cases, pressure tubes. The pressure vessel is a strong vessel or a strong series of tubes, in this diagram made of steel, that contains the reactor core, moderator, and the coolant that runs through it. It's really important that the pressure vessel be strong because the reactor core are where the most extreme conditions within the nuclear reactor are reached. The last two components of most fission reactors are the pressurizer, which in reactors that use water as their coolant keeps the water under extreme pressure so that it doesn't boil away and instead stays in its liquid form so that it can effectively cool the reactor core. And then the other component is the containment vessel, which is very similar to the pressure vessel that I mentioned earlier, except that it's around the entire reactor. The containment vessel protects the reactor from outside forces that might damage the reactor, and it also protects the outside from the reactor's regular radiation, and in the case of a meltdown, it helps to contain some of the radioactive waste that might come from the reactor. Keeping these different components in mind, we'll now talk about the different kinds of fission reactors. The vast majority of fission reactors use uranium as fuel. Most uranium reactors have a fuel mixture consisting of mostly uranium-238 with a small amount of uranium-235. This may seem odd at first glance since only uranium-235 is used for fission in most reactors as it is fissile, but it is because uranium naturally contains much more uranium-238 than uranium-235. The downside to this is that only a small percentage of the uranium fuel loaded into a reactor is ever actually used for fission, leading to almost all the fuel loaded into the reactor being loaded out as radioactive waste. Another aspect of uranium reactors is that they typically need to be completely shut down for at least a few weeks every 1 to 2 years. This may seem like a lot, but refueling is typically the only time a nuclear reactor isn't producing energy, as it doesn't usually need much maintenance. This means that nuclear reactors are only not producing energy approximately 8% of the time. An additional cool fact about many uranium reactors today is that despite only being designed to run for 30 to 40 years, many are given licensing extension as they are still in good condition after that time. Some can even run for 80 years or more. You also may not know this, but initially a neutron released from the splitting of a uranium atom is a fast neutron, called such because it has a lot of energy. However, most reactors today are thermal reactors, which means that they use moderators to slow down those fast neutrons, decreasing the energy and turning them into thermal neutrons. Thermal neutrons easily spit uranium-235, but they are only absorbed by uranium-238, which is why they can't be used for fission in thermal reactors. Only fast neutrons can split uranium-238, which may make it seem counterintuitive to have a moderator, but thermal neutrons with uranium-235 atoms happen to set up the best conditions for fissions in most reactors today. Going into specific examples of uranium reactors, by far the most common reactor today is a pressurized water reactor, with about 68% of reactors today being pressurized water reactors. These reactors use uranium fuel enriched to be 3.5 to 5% uranium-235, and they use regular water as both the coolant and the moderator. These are called pressurized water reactors because the water in the primary cooling circuit, the circuit that runs through the reactor core, is heated to 325 degrees Celsius by the core, so the coolant has to be held at 150 times the atmospheric pressure to keep it from boiling. However, if the water coolant gets too hot, which could happen during an emergency, it will start to boil away, which actually reduces the moderation in the reactor and slows down the reaction. This is a convenient safety measure to prevent a meltdown of a reactor in the event of an emergency. There are also control rods and boron that can be added to the primary cooling circuit to absorb neutrons and stop reactions further. There's also a secondary coolant circuit where water is boiled, turning it into steam, so that I can turn a turbine and generate electricity. The second most common uranium reactor, though only at 14% of all nuclear reactors, is the boiling water reactor. It is very similar to the pressurized water reactor as it also has 3.5 to 5% enriched uranium-235, and it has regular water as both the coolant and the moderator. The main difference is that the boiling water reactor only has one cooling circuit because it allows the coolant flowing through the reactor to boil into steam and thus maintains a lower pressure at 75 times atmospheric pressure with a temperature of 285 degrees Celsius. The steam produced in the reactor core flows directly to a turbine to generate electricity. A safety feature unique to this reactor is that by restricting water flow to the core, which also restricts coolant to the core, it allows more of that water to evaporate, which reduces the moderation effect and slows down the reactions in the core. The third most common uranium reactor is the pressurized heavy water reactor. The standout feature of this reactor is that it uses heavy water, water with deuterium instead of single proton hydrogen, as its coolant and moderator. Since heavy water is a better moderator than regular water, pressurized heavy water reactors can use natural uranium or recycled fuel from other reactors which have lower concentrations of uranium-235. However, regular water has to be enriched to procure heavy water, so it's a fairly equal trade-off from enriching uranium to enriching water. Other than that, the pressurized heavy water reactor is very similar to the pressurized water reactor, though this diagram represents a cooled reactor core design called a calandria. This type of reactor core consists of a multitude of pressure tubes instead of a single pressure vessel. Each tube forms a channel that fuel can be placed into, with coolant still being able to flow past that fuel. The individual tubes within the calandria allow for partial refueling without total shutdown of the reactor, and they are cheaper to make, though they have not been proven to be as durable as a pressure vessel. Two more reactor designs that aren't that common but exist are the advanced gas-cooled reactor, which I believe was mostly used in Britain, and the light water graphite moderated reactor. The light water graphite moderated reactor is kind of similar to the boiling water reactor, except it uses graphite as a moderator instead. However, this is a problem as when water boils too much, which removes coolant, it results in reduced cooling without reduced moderation, which basically means that the reaction will still go at the same rate, but it's not being cooled, which is the perfect conditions for a meltdown. The next kind of fission reactor is the fast neutron reactor. Although we already have some fast neutron reactors around, this kind of reactor is the subject of a lot of research and new and advanced technology. It is called a fast neutron reactor because there is no moderator to slow down fast neutrons into thermal neutrons, and they accomplish this by using molten metal or salt coolants as opposed to water coolant. These reactors either use plutonium or highly enriched 20% uranium-235 as their fuel, but the unique thing about this type of reactor is that they can breed more fissile fuel like plutonium-239 from fertile fuel like uranium-238 by allowing that fertile fuel to absorb neutrons. This feature of fast neutron reactors makes them 60 times more efficient with their fuel than traditional reactors, because traditional reactors, as I mentioned earlier, can't use fertile atoms like uranium-238 for energy, whereas fast neutron reactors can. For fast neutron reactors, all you have to do is just load in a little bit of fissile fuel with a lot of fertile fuel, and you'll have a self-sustaining reaction that lasts for a really long time. A convenient safety measure unique to fast neutron reactors is that as the temperature rises within the reactor, which would likely happen in the event of an emergency, the reaction slows. The biggest downside to fast neutron reactors, and the reason they are not more common, is that they are extremely expensive to build. One last fun fact about fast neutron reactors is that they are smaller than traditional reactors because they don't need a pressurized coolant, and they also don't need moderators. The next kind of fission reactor is not yet in use as it still needs extensive research. Small modular reactors are very similar to pressurized water reactors in terms of their mechanism of energy production and fuel efficiency, but as their name suggests, they are smaller. The designs for most small modular reactors are up to 1/3 the size of traditional reactors, with up to a little less than 1/3 the power output. Some designs for small modular reactors are small enough to be built in factories and put on truck beds to be shipped to where they are needed. An upside to this kind of design is that they would be standardized and would make producing a nuclear reactors cheaper. Small modular reactors are very helpful in areas without the ability to support a large reactor, and they can be on or off the electrical grid. Additionally, if more energy is needed in a particular area, you can simply build more small modular reactors at a smaller cost than it would take to have a large nuclear reactor with the same power output. Small modular reactors can also be built underground, allowing for increased protection from external events, and they have many passive safety systems that keep them running safely without human intervention for long periods of time. Since they are small, they can even be placed inside additional structures for additional protection. The small size and standardization of small modular reactors also reduces construction times and costs, and they even allow for up to 20 years without refueling. This next reactor design was actually introduced to me by my friend Clay. It is a fairly common theoretical reactor design and is called the liquid thorium fluoride reactor. The interesting thing about this reactor is that its main fuel source is thorium, a fertile element that doesn't normally sustain fission on its own. However, When it absorbs a neutron, thorium-232 turns into thorium-233, which then turns into protactinium-233 through negative beta decay, and then uranium-233 through another negative beta decay. Uranium-233 is fissile and can sustain a nuclear fission reaction on its own. This reactor is also unique in that its fuel is a molten thorium fluoride salt that doubles as the coolant and the fuel source, and it offers some unique advantages I'll discuss later. Liquid thorium fluoride reactors are different from fast neutron reactors in that they can be thermal reactors with moderators. Even though the fuel circulates through the entire reactor, not just the core, the moderator is only in the core, so it is much less likely for fission to occur outside the core where there is no moderator. An advantage of this reactor type is that thorium is much easier to mine as it is usually more concentrated than uranium and is less toxic as it doesn't give off radon gas. Thorium is even 3 times more abundant in Earth's crust than uranium, though 2/3 of that thorium is relatively hard to get to, and there's a substantial amount of uranium in the ocean as well, which evens out some of the benefits of thorium over uranium when it comes to mining. Liquid thorium fluoride reactors, as well as fast neutron reactors, produce approximately 100 times less radioactive waste, with much shorter half-lives than traditional reactors. Additionally, 1 ton of thorium in a liquid thorium fluoride reactor can produce just as much energy as 35 to 200 tons of uranium in a traditional reactor, or 3.5 million tons of coal in a coal plant. On top of all that, thorium can't be used to make nuclear bombs because it isn't naturally fissile. Just like a fast neutron reactor, liquid thorium fluoride reactors are smaller than conventional reactors because they don't need to be pressurized. The safety features of this reactor include a decreased reaction rate as the temperature of the reactor increases due to increased neutron absorption by thorium, and the meltable plug that drains the fuel out of the reactor core if temperatures get hot enough. The major downside to this reactor type is that much more research needs to be done before it is viable, as its design uses a lot of advanced technology. This next bit is a little bit arbitrary, as generations of reactors aren't clearly defined. But the majority of reactors today are currently in what's called Generation 2, as they use enriched uranium and are cooled by water. Generation 3 reactors are the ones in development today, which are very similar to Generation 2, but they have slightly enhanced safety. Generation 4 reactors include the liquid thorium fluoride reactor we just talked about, as well as the fast neutron reactor, and they improve a variety of things over Generation 3 reactors, such as having the ability to run at higher temperatures, which increases efficiency, and at lower pressure, which simplifies reactor design and makes it safer. Specifically, Generation 4 reactors like the liquid thorium fluoride reactor and fast neutron reactor can use molten salt or metal coolant. This type of coolant is good because it runs at a really high temperature through the reactor, much higher than water, which allows for a more efficient conversion of reactor heat into electricity. And it also can be at lower pressure since you don't have to keep the molten salt or metal from boiling at the temperatures that the reactor is running at. This makes the reactor less complex, smaller, and also less likely to explode. Molten salt or molten coolant also has the advantage of being able to passively cool a reactor. That is, cool a reactor when it's shut off without boiling off like water, because the boiling point of metal and salt is so far away from the melting point that it's almost impossible to happen within a reactor when turned off. A gas-cooled reactor also has the advantage of, running at a higher temperature than a water-cooled reactor, which allows for a more efficient conversion of heat to electricity. Now that I've discussed the majority of current and theoretical fission reactor designs, I'm going to talk a little bit about some fusion reactor designs. Keep in mind that no fusion reactor today has been able to produce more energy than it has consumed to initiate fusion reactions, so none of these designs have actually been used to create energy. The first type of design I'll talk about will utilize muon-induced cold fusion. Muons are extremely short-lived particles that are similar to electrons, except for the fact that they are much more massive and they are very short-lived. Because of their increased mass, if they form atoms of protons, the atoms they create have significantly smaller radii. Atoms vibrate when they form a molecule, with the nuclei moving a little closer and a little further away from each other when they do. Normal atomic nuclei don't get close enough through this vibration to initiate nuclear fusion. But the small radii of muon atoms mean that when two atoms of muons form a molecule, there's a really good chance that the nuclei of those atoms will get close enough for the strong nuclear force to pull them together. However, due to how short-lived muons are, about 2 microseconds, they are not very abundant in nature, and they need to be created for use in fusion. Since fusion happens very quickly, one muon can help many nuclei fuse together before it gets stuck in a helium atom and decays into an electron and neutrinos. The downside to all this is that it currently takes more energy to create one muon than it produces by facilitating fusion. The next type of nuclear fusion I will be discussing is magnetically confined fusion. This type of fusion utilizes a reactor design in the shape of a torus, practically a donut. The torus contains the plasma that will be utilized to facilitate nuclear fusion by using magnetic fields to contain the charged particles that make up the plasma. The two most popular designs for this type of reactor are the tokamak and the stellarator, that differ mainly in how the magnetic field containing the plasma is generated and how that magnetic field shapes the plasma. The tokamak, shown here, is simpler than the stellarator, but the stellarator, shown here, makes up for its increased complexity by offering a few benefits over the tokamak. In order for this type of reactor to work, the plasma must be at extremely high temperatures, approximately 150 million degrees Celsius, and very high pressures. However, with both high temperature and pressure, nuclear fusion occurs. Most reactors of this design have been for research only, but the International Thermonuclear Experimental Reactor is a reactor being built in France that will be the largest of its kind ever built. It will utilize a tokamak with the goal of producing more energy than it consumes to start the nuclear fusion process. If the International Thermonuclear Experimental Reactor works, however, it will utilize one of the most powerful sources of energy we know. This is because nuclear fusion reactions release 4 times as much energy as fission reactions when comparing mass of fuel used. Additionally, the fuel for magnetically confined fusion reactors can easily be obtained from seawater and lithium, as deuterium and tritium respectively can be harvested from them. Another upside to this kind of reactor is that its main waste is helium, an inert gas unlikely to have a significant effect on the atmosphere. The only potential radioactive waste from these reactors is tritium, but it only has a half-life of 12 years, far shorter than the nuclear waste of fission plants, and tritium is actively consumed during fusion reactions. However, again, the problem with these reactors is that up to this point, they've consumed more energy than they produced. This next kind of fusion reactor, the inertial confinement fusion reactor, can either be direct or indirect, but either way, powerful lasers are used to heat a pellet of deuterium and tritium, which compresses the pellet via an explosion on the surface of the pellet from the high heat of the lasers. This explosion not only creates outward force, but also an inward force that pushes the inside of the pellet together so hard that enough pressure and heat is created to initiate a nuclear fusion reaction. It is called inertial confinement because the energy from the initial nuclear fusion in the core spreads throughout the entire pellet's capsule, starting more nuclear fusion reactions faster than the capsule can be blown apart, allowing for a complete nuclear fusion chain reaction to take place. This is the same process that occurs in hydrogen bombs, but it would be used on a much smaller scale in these reactors. The final major candidate for fusion reactors on Earth was discovered by NASA and is called lattice confinement fusion. The basic idea behind this reactor is using the lattice of a large metal atom, like erbium, to constrain the small atoms of deuterium. Such confinement brings deuterium atoms really close together, allowing for a deuterium density 1 billion times greater than that inside tokamak plasma, and it produces stable and enhanced nuclear reactions. Fusion reactions start when X-rays are used to split deuterium nuclei into energetic protons and neutrons. Neutrons then collide with static deuterium can give it enough energy to fuse with other deuterium. This produces either helium or hydrogen nuclei with 3 nucleons, and there is a leftover neutron to cause more reactions. Now that I've discussed all these different kinds of reactor designs, I'm going to put in one last little bit about how they compare to each other. Now obviously this video is already really long, and by going over every single number in this table I would make it even longer, so I'm going to just give you the big ideas of the table and of my research. So obviously the pressurized water reactor is ranked the lowest because it's the most primitive of all the reactor designs, and all the other reactor designs have been specifically made to improve upon the pressurized water reactor in some way. However, I still believe that they are better than renewable energy sources and fossil fuels, as I said in my last video on the Hilliard-Davidson Environmental Awareness Club channel, which you can go watch to get my opinion on that. The reason the fast neutron reactors are ranked the highest is because they are either equal to or greater than all the other reactors in every single category, but they could be implemented faster because we have some fast neutron reactors in use today, not a lot of them, but we do, and they do utilize some advanced technology, but it would be relatively short period of time to implement those type of reactors versus a liquid thorium fluoride reactor, for instance, or even longer, a fusion reactor. While we would be waiting for those types of fast neutron reactors to be researched and built, I believe that the pressurized water reactor with accident-tolerant fuel, which if you go back to the chart is the last row, would be a good way to improve the reactors we have now. So accident-tolerant fuels, all those are, they increase fuel efficiency, they reduce the amount of radioactive waste by increasing fuel efficiency, they, most importantly, increase safety, and they have a few other little benefits over regular fuel for pressurized water reactors. But that oxidant tolerant fuel would go a long way to improving the reactors we have in use today, and those would really help until we can get fast neutron reactors built and online. The reason that liquid thorium fluoride reactors aren't higher up is because they're more or less similar or the same to the fast neutron reactors in every category, except, again, it would take longer to build them and implement them. And then the small modular reactor, while very similar to the pressurized water reactor in many ways, making it just as wasteful and sometimes just as dangerous, it does have a very niche use that would be very useful for smaller communities and areas that can't support large nuclear reactors. So I do believe that the fast neutron reactor, the liquid thorium fluoride reactor, and the small modular reactor all have places and uses in the future, with the pressurized water reactor with accident-tolerant fuel kind of holding us off until then. And then finally, the International Thermonuclear Experimental Reactor, which represents pretty much all fusion reactors. I believe it's ranked kind of low in this table because it would take so long to get right. But once we do have fusion creating more energy than it consumes, I do believe that fusion is the future of energy because it is inherently more powerful than fission. And since fission's already more powerful than a lot of renewables and fossil fuels, as I discussed in my other video, it just makes fusion one of the best sources of energy that we know of. So fusion is definitely, in my mind, the future of energy. Thank you so much for sticking with me all throughout this video. I know it was a long one, I'm going to admit it. The animation quality wasn't quite as good as I was hoping it would be, especially since I had to back up all of my drawings last minute when we had to turn in our school iPads at the end of the school year. So again, thank you so much for sticking with it. I hope you enjoyed learning about nuclear reactors, and please subscribe to this channel, as I'm going to try and make at least one more video about nuclear radiation itself, and kind of inform you a little bit about it so that you can make a more informed decision on if you like nuclear reactors or don't like them based on how harmful nuclear radiation actually is.